Hey guys, and welcome to this video on some other ways to graph lines. So here we go. Alright, so let's start by graphing all of the solutions to 3x plus 5y equals 30. And so I'm going to let you put this into slope-intercept form and graph it. So why don't you pause the video and do that, and we will reconvene afterwards. Alright, so not so bad. Once you put it in a slope-intercept form, we found that our y-intercept was 6, and our slope was negative 3/5, meaning every 5 units we went to the right, we went 3 units down. We were able to find a whole bunch of points and sketch our graph. And we also found our x-intercept of 10, which was very clear from our graph. Now my claim is that for this equation, there's actually a much easier way to graph it accurately and quickly. So note, because we're trying to graph a line, all we need are 2 points. And once we have 2 points, we can extrapolate that pattern in either direction and come up with an accurate graph for our line. So, how do we find 2 points given this original equation? Well, my claim is, why don't we just find the x-intercept by setting y equal to 0, and find the y-intercept by setting x equal to 0. So why don't you quickly pause the video and find each of those from this equation. So now that we've got our x-intercept and our y-intercept, that's all the 2 points that we need to know what our graph is going to look like. Let's connect them and extend our line in both directions. And while in this example, we went through the trouble of actually using our equation and explicitly writing out how we solved for our y-intercept and x-intercept, I'm sure just by looking at this, you could have found the x-intercept and y-intercept in your head, no problem. So just another way of quickly and accurately graphing these lines without having to put the equation in slope-intercept form. Alright, now let's graph all of the solutions to 3a minus 2b equals 6. And in our first example, we're going to let a be the dependent variable. And in our second example, we're going to let b be the dependent variable. Now, what's really nice is that no matter what's the dependent variable or what's the independent variable, finding the intercepts is no different. And I'm sure you can tell very easily looking at either of these equations, if we set b equal to 0, we're going to just end up with 3a equals 6, leaving a equals 2. So of course, our a-intercept is going to be 2. Likewise, if we set a equal to 0, then we're just going to be left with negative 2b equals 6, and of course, b will equal negative 3, meaning our b-intercept is negative 3. So let's go ahead and label our axes accordingly and graph our intercepts accordingly on both these pairs of axes. And now in theory, because we have 2 points, we can connect them and extend our line to make our graph. Now, because these two intercepts are relatively close to one another, what I would suggest is finding the pattern of how the dependent and independent variable changes between them and then extrapolate that in both directions. So for instance, in our first one, where a is the dependent variable, it appears that every 3 units we move to the right, we move 2 units up. So let's go ahead and extrapolate that in both directions. And for our graph on the right, it appears that every 2 units we go to the right, we go 3 units up. So again, let's extrapolate in both directions. And recall, I know these two graphs look slightly different from one another, but that's because we switched what was a dependent variable and independent variable. In fact, they both capture the exact same relationship. They both capture all of the infinitely many solutions to 3a minus 2b equals 6. And what I'd like to do is put both of these in a slope-intercept form, one with a being the dependent variable, one with b being the dependent variable, just to show that our graphs absolutely are accurate. Alright, let's practice by graphing all the solutions to 5h plus 2k plus 20 equals 0, and in this one we're going to let h be the dependent variable, and all the solutions to negative 5x equals 40 minus 8y. And let's graph these solutions just by finding the intercepts, finding the difference between them, and extrapolating to create our graph. And when you're done, we might as well put both of these equations into slope-intercept form just to make sure we did everything correctly. Alright, here's an equation that's going to prove a little bit more difficult than the ones we've done so far. Now, before we define which variable is our dependent variable and which one is our independent variable, let's just go ahead and find the g-intercept and d-intercept. So please pause the video and find those two intercepts. So in this case, we found that our g-intercept was 3, that's nice, but our d-intercept was negative 9/4, or as a mixed number, negative 2 1/4. Now I'm sure we could do a pretty good job eyeballing that on our graph, but in general, we want to try to graph as accurately a graph as possible, and so eyeballing just isn't part of the equation. Now why is it that this equation didn't have two nice intercepts, but all of the other equations we did so far did have two nice intercepts? Note, in all of the other equations, all the coefficients were all factors of the constant in the equation. 3 and 5 were factors of 30. 3 and 2 were factors of 6. 5 and 2 were factors of 20. 5 and 8 were factors of 40. But in this one, 3 is a factor of 9, that's why we had a nice g-intercept, but 4 is not a factor of 9, and that's why we got a d-intercept that wasn't so nice. In general, using the intercepts method to graph a linear function will work best when both of the coefficients on the variables are factors of the constant in the equation. So it looks like we're going to have to graph this using the slope-intercept form. Now the question is, what should be our dependent variable and what should be our independent variable? Well, note, if we solve for d and make d our dependent variable, we're going to have a d-intercept of negative 9/4, and we're not going to even be able to graph that without eyeballing. But if we solve for g and make g our dependent variable, we'll get a nice g-intercept of 3. And no matter what the slope is, no matter what kind of fraction, positive, negative, whatever the slope is, we can handle it as long as we have that nice intercept to start from. So, if we look at an equation and it's not the case that both of these coefficients are factors of the constant, it'll be best to put the equation in a slope-intercept form by solving for the variable whose coefficient is a factor of the constant, in this case g. So let's make g our dependent variable, put this in a slope-intercept form by solving for g, and graph. Alright, so in this case, we had to put the equation in a slope-intercept form. Now note, before we found a d-intercept of negative 9/4, about negative 2 1/4, and when we zoom in on our graph, that's absolutely confirmed. Alright, let's practice that last skill by graphing all the solutions to negative 5w plus 4h equals 12. So you decide which variable should be the dependent variable, put it in slope-intercept form, and go ahead and graph this equation. Alright, two more last examples of some kind of tricky looking equations for us to graph. Now they're both definitely going to be lines because they satisfy all of the requirements for an equation to have a graph that's a line. But what are they going to look like? So let's think about the equation y equals 6. Now, there's no x in that equation at all. Now, if we wanted to, we could consider this y equals 6 plus 0x, and that might help us out. Now, it's clear that if x were 0, y would be 6. So our y-intercept is definitely 6. But what about our x-intercept? Remember, the x-intercept happens when y is 0. But y is equal to 6. Y can never be 0. It's always 6. So what does that mean? If we have a line that, of course, goes on and on forever and ever in both directions, but it never hits the x-axis, that means it has to be parallel to the x-axis. And so the graph for the equation y equals 6 is going to be a line parallel to the x-axis going through the point 0, 6, because that's our y-intercept. And in fact, whenever we have an equation of the form dependent variable equals a constant, just some number, then it's going to be a horizontal line. And of course, the slope of a horizontal line will always be 0. And here are some examples of these horizontal lines. Alright, last one. Let's graph all the solutions to the equation x equals -3. Now in this equation, we don't have any y's. Well, at least I'm sure we can agree that the x-intercept is going to have to be -3. But what about the y-intercept? The y-intercept happens when x is 0, but x is -3. It's never 0. It's always -3. So this equation, when we graph it, has no y-intercept. And so if this line, which goes on and on forever and ever in both directions, never intersects the y-axis, that means this line has got to be parallel to the y-axis. So the graph of the equation x equals -3 is going to be a vertical line parallel to the y-axis going through the point -3, 0, which is our x-intercept. And in general, whenever we have an equation of the form independent variable equals a constant with no variables, just a number, that graph is going to be a vertical line. And the slope of a vertical line, many people are tempted to say that the slope of a vertical line is infinitely large, but in fact, we say that the slope of a vertical line is undefined. And here are some examples of those vertical lines. That's it for this video, guys. I hope you found it helpful, and I hope you enjoyed.